Welcome back, deep divers. Ready for another plunge into the mysteries of the cosmos? Today we're diving into a world where dark matter, black holes, and gravitational waves all come together.
It's a pretty wild combination.
You can say that again.
Yeah.
So picture this. You've got two galaxies merging.
Happens all the time, right?
Right. And at the heart of these galaxies, you've got these supermassive black holes, millions or even billions of times heavier than our sun, and they're locked in this cosmic dance, spiraling towards each other.
And as they spiral, they send out these ripples in space-time gravitational waves.
Which we can actually detect now. Isn't that amazing?
It's incredible. But here's where things get really interesting.
No, I'm all ears.
This cosmic dance might not be a solo performance. Dark matter could be playing a hidden role.
Dark matter. The stuff we can't even see.
Yeah.
How can it influence these massive black holes?
Well, that's what this deep dive is all about. We're exploring a paper called Scattering of Wave Dark Matter by Supermassive Black Holes, and it suggests that dark matter doesn't just passively exist around these black hole binaries.
Uh-oh, so it's not just sitting there quietly.
Nope, it might be actively influencing them through a process called scattering.
Scattering. Okay, you're going to have to break that down for me.
Imagine, instead of thinking of dark matter as individual particles, think of it as a wave spread out across vast distances.
A wave, like whoo, whoosh.
Exactly. And this wave, dark matter, doesn't just orbit the black hole binaries, it actually gets scattered off them.
Okay, so instead of just going with the flow, it's bumping and bouncing off these black holes.
You got it. Think of it like ripples on a pond hitting a spinning paddle. It creates this unique pattern.
I can almost picture it. But how does this scattering actually work? Is it happening constantly?
Well, it's especially pronounced at certain resonant frequencies.
Resonant frequencies. That rings a bell. Like when you strike a tuning fork and it vibrates strongly at its specific frequency, right?
Precisely. Now imagine the black hole binary's orbital frequency acting like that tuning fork.
So when it matches certain dark matter resonances, the scattering gets amped up.
Exactly. It's like everything syncs up and the energy carried away by those scattered dark matter waves peaks.
Fascinating. So it's not just a constant scattering. There are these moments where it goes into overdrive.
Mm-hmm.
But how can we actually observe this? We can't see dark matter.
Right, we can't see it directly. But here's the exciting part. We might be able to hear its echo, so to speak, through gravitational waves.
Gravitational waves. How?
Well, the scattered dark matter can actually act like a sort of cosmic drag on the black hole binary, subtly changing how they spiral inward.
Cosmic drag. You're losing me again.
Okay, imagine trying to swim through a pool filled with thick syrup. You'd feel a lot of resistance, right?
Yeah, I can imagine that.
Well, it's similar to what's happening here. The scattered dark matter creates this dynamical friction that slightly slows down the black holes in spiral.
So the black holes are doing their cosmic dance, but the dark matter is making them drag their feet a bit.
Exactly. And because their in spiral is affected, the gravitational waves they emit also change.
So we could detect this dark matter scattering by looking for those subtle changes in the gravitational waves.
That's the idea. It's like listening for the echo of dark matter in the symphony of gravitational waves.
So we're essentially trying to eavesdrop on this cosmic dance floor and hear the whispers of dark matter.
You got it. And if we can do that, it would be a major breakthrough in our understanding of dark matter and its role in the universe.
This is already blowing my mind, but I have a feeling we're just getting started.
Oh, there's much more to come. There's definitely more to this story. This research also touches on this long-standing puzzle in astrophysics called the final parsec problem.
The final parsec problem. Okay, that's a new one for me. What is that all about?
It's this mystery surrounding how supermassive black holes actually get close enough to merge. Our models suggest they should spiral inwards pretty efficiently, but then something seems to slow them down in the final stages.
So they hit a cosmic speed bump right before the grand finale.
Yeah, you could say that. And that's where this dark matter scattering might come in. This dynamical friction it creates could explain this slowdown.
So this research isn't just about dark matter. It could also help us solve this final parsec problem. That's amazing.
Yeah.
But how do scientists actually study these events? It's not like we can just fly out to a black hole and watch the dark matter scattering in action.
Definitely not. We rely on those gravitational waves we've been talking about. They act as messengers carrying information about events happening near those black holes across vast cosmic distances.
So by studying these gravitational waves, we can figure out what's happening in those extreme environments.
Exactly. We analyze their frequency, their amplitude, how they change over time. All these details help us piece together the dynamics of those systems.
And this includes figuring out if dark matter is playing a role.
You got it. Remember those resonant frequencies we talked about earlier? Well, the paper suggests those resonances could leave a distinct signature on the gravitational wave signal, like a bump or a dip in the data.
Would you say this signature is unique to dark matter scattering, like a cosmic fingerprint?
That's a great way to put it. Now, the strength of this signature, how pronounced those bumps or dips are, depends on a few things. One is the mass of the dark matter particles themselves.
Okay, so heavier particles would create a stronger signature.
Actually, it's the opposite. With wave dark matter, the lighter the particles, the more pronounced their wave-like behavior and the more efficiently they scatter.
So by looking for these signatures in gravitational waves, we could not only confirm that dark matter scattering is happening, but also get clues about the mass of the dark matter particles involved.
Precisely. It's a powerful tool for probing the nature of dark matter. Another important factor is the density of the dark matter around the black hole binary.
So a denser cloud of dark matter would mean more scattering, and therefore a more noticeable signature in the gravitational waves.
Exactly. And galactic centers, where these supermassive black holes live, are thought to have some of the densest concentrations of dark matter in the universe, making them prime locations for observing this phenomenon. But there's another layer of complexity: the speed of the infalling dark matter.
Infalling dark matter. Shouldn't it all be orbiting the black hole?
While some dark matter orbits, a significant portion is also falling directly towards the black hole. The paper specifically focuses on the scattering of dark matter with zero angular momentum.
Angular momentum. Can you remind me what that is again?
Basically, it describes how much the dark matter is swirling around the black hole as it falls in. The paper focuses on dark matter falling directly in without that swirling motion.
Got it. So they're looking at dark matter on a direct collision course with the black hole.
Exactly. And this simplification allows them to make some concrete predictions about the scattering process. They find that this scattering is most efficient when the dark matter's de Broglie wavelength is comparable to the separation between the two black holes in the binary.
De Broglie wavelength. Okay, I'm not familiar with that one.
It's essentially the wavelength associated with the particle, and it's particularly important when we're talking about wave-like behavior.
So it's like there's this sweet spot where the size of the dark matter wave matches up perfectly with the size of the black hole system.
Exactly. And when that happens, the scattering becomes much more pronounced, leading to a stronger signal in the gravitational waves.
Okay, so we've got the mass of the dark matter particles,
Yeah.
their density, their speed, and even the size of the black hole system. All these factors influence how efficiently the dark matter scatters and how easy it might be to detect.
You got it. But we can't forget about the environment around these black hole binaries.
Right, black holes aren't just floating in empty space. What kind of environment are we talking about?
Well, galactic centers are these dynamic environments filled with stars, gas dust, and all sorts of other stuff. This cosmic clutter can influence how dark matter behaves and how it interacts with black holes, making things more complex to study.
So it's not just a clean, isolated system we have to account for all this cosmic clutter.
Precisely. And that's where things get challenging. We need sophisticated simulations that capture the intricate dynamics of these messy environments to fully understand what's going on.
It sounds like a daunting task. Are we up to the challenge?
Absolutely. This is cutting-edge science, and we're constantly developing new tools and techniques. It's a truly collaborative effort with experts in astrophysics, cosmology, particle physics, and computational science all working together.
That's impressive. But I'm sensing a but coming.
You're right.
Yeah.
While this research offers an exciting glimpse into the potential of using gravitational waves to study dark matter, we're still in the early stages.
So we're not quite ready to declare victory in the search for dark matter just yet.
Not quite. There are still challenges ahead. One is the sensitivity of our current gravitational wave detectors. They're not quite sensitive enough to pick up those subtle signatures predicted by this research. We need even more advanced instruments like the proposed space-based LISA mission.
Alas, tell me more about that.
LISA stands for Laser Interferometer Space Antenna. It's an incredibly ambitious project, a giant gravitational wave detector in space, made up of 3 spacecraft millions of kilometers apart.
Wow, a space-based gravitational wave detector. That's next level stuff. What makes LISA so special?
It all comes down to sensitivity. LISA will be able to detect gravitational waves at much lower frequencies than our current ground-based detectors, opening up a whole new window into the universe.
So it's like getting a brand new telescope that can see a wider range of the electromagnetic spectrum.
You could say that. And this enhanced sensitivity will be crucial for detecting those subtle signatures of dark matter scattering.
Yeah.
But even with LISA, it won't be easy. Remember all those complexities we talked about, the dark matter mass density speed, the messy environment? All these factors will create a lot of noise in the data, making it difficult to isolate the signal we're looking for.
So it's like trying to hear a pin drop in a rock concert. We need some serious filtering to find that signal.
Exactly. We'll need to rely on advanced data analysis techniques and sophisticated theoretical models to separate the signal from the noise.
So it's not just about building bigger and better detectors. We also need to sharpen our analytical tools.
Absolutely. It's a multifaceted challenge, but that's what makes this feel so exciting. It's pushing the boundaries of our understanding and driving innovation in both technology and theoretical modeling.
It sounds like this research had the potential to completely revolutionize our understanding of dark matter and its role in the universe.
It does. And this is just the beginning. As we continue to refine our models, improve our data analysis techniques, and develop even more sensitive detectors, who knows what other amazing discoveries await us.
This has been an incredible journey so far, and I'm already eager to see what the future holds for this field. But before we get ahead of ourselves, there's one more aspect we need to explore: the potential implications of this research for our understanding of gravity itself. Gravity. Wow, okay, now you're really taking this deep. I thought we were focusing on dark matter and black holes. How does gravity fit into all of this?
Well, it's all connected, really. Our current understanding of gravity is based on Einstein's theory of general relativity. And it's been incredibly successful, explaining all sorts of things.
Like what? Give me some examples.
Well, it explains how light bends around massive objects, and it explains the expansion of the universe. But even Einstein's theory has its limits.
So you're saying even Einstein didn't have all the answers. There are things his theory can't explain.
There are a few mysteries it struggles with, yeah. For example, general relativity doesn't fully explain the accelerated expansion of the universe, which we attribute to dark energy.
Right, dark energy. Always a bit of a head scratcher.
And another thing is, the theory doesn't quite have all the answers when it comes to how gravity behaves at extremely small scales, like near a black hole's singularity.
Okay, so there might be some cracks in the foundation of our understanding of gravity.
Yeah.
But how does this research on dark matter and black holes relate to those cracks?
Well, that's where things get really interesting. If we can actually detect those subtle signs of dark matter scattering in gravitational waves.
Right. The ones we were talking about earlier.
Yeah, exactly. It could suggest that our current understanding of gravity needs a little tweaking.
So you're saying those gravitational waves might be giving us clues about not just dark matter, but about gravity itself, the very force that governs the universe.
Precisely. It's like those waves are whispering secrets about the deepest mysteries of the cosmos.
This is blowing my mind. We're talking about potentially revolutionizing our understanding of both dark matter and gravity.
Mm-hmm.
What are some of the alternative gravity theories out there? What are physicists exploring?
Oh, there are some really fascinating ideas out there. Some theories suggest that there might be extra spatial dimensions beyond the three that we can perceive.
Whoa, extra dimensions. That sounds pretty wild.
It does, doesn't it? And then there are others that propose that gravity might not actually be a fundamental force.
Wait. If gravity isn't a fundamental force, then what is it?
Well, some theories suggest it could be an emergent phenomenon that arises from some deeper underlying principle that we haven't quite grasped yet.
Emergent gravity. Okay, now we're really getting into the theoretical weeds.
I know, right? But that's what's so exciting about science. It constantly pushes the boundaries of our imagination and forces us to think beyond our current understanding.
I have to say, this research has the potential to be truly groundbreaking. It's not
Good.
just about filling in the gaps in our knowledge. It's about potentially rewriting the textbooks on gravity and the universe itself.
It really is, and we're just at the very beginning of this incredible journey of discovery. Who knows what other amazing insights are waiting for us as we continue to explore the cosmos with more and more precision.
It's mind-boggling to think that those tiny, subtle changes in gravitational waves could hold the key to unlocking such profound mysteries. So what does this all mean for you, our deep diver? If we can detect these changes in gravitational waves, it could be the confirmation we need that dark matter isn't just out there. It's an active player in the universe, shaping galaxies and influencing the fate of black holes. And who knows, it might just hold the key to a deeper understanding of gravity itself. So keep looking up, deep divers, because the universe is full of surprises just waiting to be uncovered.